Shalom and welcome everyone. I want to welcome you once again in joining me in Checkpoint Training Bites. Checkpoint Training Bites is where we bring you advanced training on Checkpoint products, features, and blades. In this module, we're going to discuss what the firewall is, and we'll talk about the different components that make up the firewall. And so now, before we get started, let's take a few moments to discuss the agenda of this module. First, we're going to start this module by talking about our Checkpoint firewall software. Specifically, we will discuss our firewall code and how it functions. Then, we will discuss how our firewall code will be installed, how it's installed in various operating systems kernels, and amongst the different hardware appliances. And here, we will discuss how the firewall works in routing mode, and I will show you where in the kernel the firewall inspection engine is injected, and where in between OSI layers the packets are being processed. And then finally, we'll put all these concepts together and discuss how Checkpoint packet filtering firewall works and how a packet is processed and matched according to the firewall's rule base. In this training module, we'll continue with our firewall discussion, discussing the Checkpoint firewall. As you know, the company name is called Checkpoint Software Technologies, and so we are a software company. Even though we make our own hardware, our software can run on multiple versions of operating systems and run on multiple third-party hardware. And so in this module, I want to start off by talking about a firewall code, which is also called the inspection engine. Checkpoint is a software firewall code that can be installed on multiple operating systems. In the past, this firewall code has run on multiple operating systems such as IBM and Sun Solaris and many other obsoleted operating systems of the past. But today, we can install it on multiple flavors of Windows operating systems, Red Hat Linux, and Crossbeam OS. And in addition to Checkpoint's fully owned and developed operating systems. Checkpoint currently has 3 operating systems. 2 are Linux-based and 1 is Unix-based. The Linux-based, we have Splat and Gaia. For Unix-based, we have IPSO operating system. But both IPSO and Splat operating systems are end of life, and so in the future, Checkpoint will only continue to support the Gaia flavor. But regardless of which operating system you have, the point I'm trying to make is that you need to have some kind of operating system running on some hardware. And when you install the firewall code, the inspection engine will get installed into the kernel component of the operating system. And so to help clarify this point, let me use 3 examples. First, you have Windows running on the Dell hardware. Second, you have Red Hat operating system running on IBM appliance. And third, you have Gaia running on Checkpoint's own 4,000 appliances. And so first you need to install the operating system on some kind of hardware. And on top of these operating systems, you want to install the Checkpoint firewall code. And so during the installation process, the firewall code, the inspection engine, gets installed into the kernel, into the operating system component of the kernel. And so this firewall code, this inspection engine, gets installed deep down into the operating system's kernel. And so it actually modifies how the Windows and Red Hat kernels operating system behaves and functions. And so this firewall code will be injected into the kernel just above the NIC drivers and before the routing engine of the operating system's kernel. And so it's important to fully understand where the firewall code is running in the kernel. It is running between the layer 2 and layer 3 of the protocol stack. And so no packets will get passed to the network layer on the firewall unless the firewall rule base accepts it first. And only then, after it has been inspected by the firewall kernel module, will the packet be forwarded to any higher layer to be routed if need be, or to be processed by the firewall application layer if the packet was destined to the firewall application processes. And so let me explain this in another way. Before talking about the firewall, let's take a look at a packet as it's being processed by a router. Let's look at what happens to a whole packet from layer 1 to layer 7 as it's being processed by a router, and then afterwards we'll look at how a packet is being processed by the firewall. And so here we have a router without the firewall code. You see, our firewall under the hood is really a router. And so once you have properly configured a router, then you can install the Checkpoint firewall code. In fact, many times I will disable the firewall code so that the appliance will act just like a router. just to be sure and to confirm that the IP addresses and the interfaces are configured correctly, and that I have properly configured the routes. And if routing is working properly, then and only then will I re-enable the firewall code. So first, I just want to be clear that we have a full understanding of how a router works. Just to be sure, we have a full understanding of all the router's capabilities and features before we install the checkpoint firewall code. And so here we have a router, and a packet is coming in on the wire towards the router. Layer 1 is the electronic bits pulsating on a wire, and so the router does not see this layer. These bits need to be assembled by the hardware NIC drivers into what we call the payload. And so the payload contains the whole packet from layer 2 all the way up to layer 7. And so the electronic signal is moved from the physical layer up to the data link layer. And the data link layer contains the layer 2 NIC code drivers, which will need to process the bits into a frame. And so then the data link layer will need to process the payload by reading the layer 2 frame header and trailer information. And so if the MAC address matches the router's MAC address, then the router will need to process the packet. But if the MAC address does not match the router's MAC address, then it will need to drop the packet. Unless, of course, it's a broadcast MAC address, in which case all machines will need to process this packet. And so in our example, the packet does match the router's MAC address. And so the router will need to process the packet. The router will need to encapsulate the packet, which means it strips out the layer 2 information and then moves up the packet up to the next layer, to the layer 3, which is the networking layer. And then the networking layer will need to process the layer 3 packet header information. And so if the destination IP address is not the router's IP address, then it will need to look in its routing table to see where to send the packet. Does it send it to the next hop router or to send it to the default gateway? Well, that depends on what is found in the routing table. If it has a route, it will need to forward it to the next hop. If it does not have a route, then it will need to forward it to the default router, which is the path of last resort. But if it finds a route in the routing table, then the routing engine will forward a packet to the interface that leads to the next hop router. And if it does not find a route in the routing table, then it needs to forward a packet to the default router. The only other exception is if the destination IP address is the firewall's IP address. And so if that destination IP address is the firewall's IP address, then the networking layer will need to decapsulate the packet and move it up to the next layer, which is the transport layer. The layer 4, which will check the segment's header information to identify if it's a TCP or UDP protocol, and also verify the port to identify what application to send the packet to. And so in our example, let's say that the payload is a TCP packet, which is destined for port 80, which is the router's HTTP web server process. And so the transport layer will again decapsulate the segment header and send the payload to the session layer, and then the session layer will again decapsulate the payload and send it next to the presentation layer, which will again decapsulate the presentation header, and finally it will send the payload to layer 7, which is the web server's application layer. And then the web server application will need to read the data contained in the final payload. And obviously, the web server application will also need to process the data and possibly reply to the packet it received. And so the reply will need to be re-encapsulated once again, and the packet is moved back down the OSI layer. And so the web server's reply will need to re-encapsulate the data back down the OSI layer. And so first, the web server will send the reply packet to the layer 7, which will add the application header, and then move the packet down to layer 6 to the presentation layer, which will add the presentation header. And then the payload is moved down to layer 5, which will add the session header information, and then it's encapsulated again down to layer 4, which will add the transport header information, like the source port, the destination port information, thereby creating the TCP segment. And then the segment is then encapsulated again down to layer 3 to create the packet's network layer information by adding the source and destination IP address. And so at this point, it will need to check the routing table to see what interface to forward the packet through. And depending on the routes, it will need to resolve the MAC address information in order to create a frame to be forwarded to the next hop. And so before moving the packet down to the layer 2, it will need to resolve the MAC address information for the frame. And so it either has the MAC address information in its ARP table, or if it does not, You must formulate an ARP request for the next hop, and once it receives an ARP reply, it will add the MAC address information into the layer 2 frame and then sends it out the interface onto the wire into electronic bits, and then this packet is forwarded on its way to its final destination. And so at each hop, the router will decapsulate the packet up to the network layer and then recapsulate the packet down to the physical layer and forward the packet on its way. And so up until now, what I just described is just basic TCP/IP routing class 101. And so there's really basically nothing new so far. And this decapsulating process is repeated on every router along each hop until the packet reaches the final destination. But now let's add the firewall code. Let's add the firewall code back into the kernel. As mentioned, the firewall code sits in between layer 2 and the layer 3. The layer 2 is where we have the network device driver code, and the layer 3, this is where the routing engine sits. And now the firewall code, by default, will drop all packets. It's the firewall's job to drop everything, unless you specifically allow it in a rule base. And so if there is no rule allowing the traffic will be dropped. Only if you allow the traffic in a rule base will the traffic be allowed through the firewall and then forwarded up to the layer 3 stack for routing. And so now let's take a look at a packet filtering firewall. First, let's take a look at the same packet as it's being processed by a packet filtering firewall. And so when a packet arrives on the wire, it arrives in electronic bits. And these electronic bits are assembled into a frame at the layer 2, the data link layer. And then the firewall matches the frame's MAC address with the firewall's MAC address. And if it matches, then it moves the packet up to the next layer. But look at this. The firewall sits in between layer 2 and layer 3. So the router cannot route it or process it before it is allowed by the firewall rule base. And so first thing that the firewall does, it looks in the rule base to see if there's a rule that matches this traffic. If there is no rule to allow the traffic, then the firewall must drop the packet. Because that's what the firewall does. The firewall must drop everything that's not explicitly allowed in a rule base. And so let's assume in this case that the firewall does have a rule to allow this traffic. And so if there is a match in rule base, then the packet is accepted. And then it moves the packet up to the next layer, to the layer 3 layer. And then again the layer 3 will need to route the packet or forward the packet up the OSI layer, whatever the case may be. But note, and an important point that I need to stress is that if the packet is decapsulated and moved up to the OSI layer, to the application layer, then the reply must come down again. And then when moving the packet from the networking layer down to the data link layer, it must again match the firewall's rule base to see if there is a rule allowing a reply. And so there must be a rule in the rule base allowing a reply, with the source being the firewall and the destination to be the original client's IP address. But in the other case, if the packet needs to be forwarded out another interface, then as mentioned before, the firewall sits in between layer 2 and layer 3. And so it will again need to be processed by the firewall code on the outbound interface. And so the firewall is always inspecting the packet twice. Once on the inbound interface, and again on the outbound interface. I know this seems extreme, but this is how Checkpoint Firewall Inspection Engine works. One other point that I want to stress is that this is the same firewall. This is the same firewall inspection engine. But it's inspecting on both interfaces. It's inspecting on the internal interface, and it's also inspecting on the external interface, using the same policy, the same inspection engine. In Checkpoint's older days, you could choose if you wanted the inspection to be done either on the inbound interface or to be done on the outbound interface, or you could have it inspected on both interfaces. Just to clarify this, there used to be an option in Smart Dashboard to inspect either on the internal interface or external interface or both interfaces. That option no longer exists today. And so the request packet must be inspected twice, both inbound and outbound. And so the reply must also be inspected twice, both inbound and also outbound back to the client. And so let me now take a moment to recap packet filtering inspection firewall. There are two main points to remember. First, you need to have two rules. One rule is to allow traffic from the source to the destination, and the second rule must allow the traffic from the destination back to the original source. And the second point is that the packet must be inspected twice in both directions. First, the request packet is inspected on the inbound on the internal interface, and then the inspection is again done outbound on the external interface. And then the reply must also be inspected twice. First, the reply is inspected inbound on the external interface, and then again it's inspected outbound on the internal interface. And then one final point that I need to mention. Now, I have been talking about the fact that you need to have a rule to match the packet in order for it to be accepted. But what exactly is being matched? What does matching the packet mean? And so when a client sends a packet to the server, it is going to encapsulate the packet through its own OSI layer, from the data all the way down to the electronic bits and signals. And so these bits on the physical wire contain all the information for the OSI payload, like the MAC address in a frame payload, and like the IP address of the packet payload, and also the ports in a segment payload. And so, since this packet is not destined for a firewall, but is destined to a web server, and so the client will need to send it to its default gateway. And so the frame contains the MAC address of the firewall, which is the client's default gateway. And so since the frame contains the firewall's MAC address, the firewall will need to pass it up to the layer 3. But it cannot do that unless there is a rule that matches and accepts the packet. And so first, the firewall needs to read the packet's IP address, the layer 3 information of the packet, before it even sends it to its own OSI layer 3 layer. And so it's viewing the packet layer 3 header information, the source IP address, the destination IP address of the packet, and then it needs to compare it to a rule that it has. It needs to find a rule in the rule base with the same source IP address, the same destination IP address that matches this packet. But not only that, it also needs to read the layer 4 information. It needs to see the source port and destination port. And it needs to match a rule that also matches the destination port. And so all three tuple information need to be matched: the source IP address, the destination IP address, and the destination port. But we don't need to match the source port, because the source port is ethereal, which means it is dynamic and always changing. And if all the three tuple information matches a rule, and the action is to accept the packet, then the packet is forwarded up the OSI layer to the layer 3, which then needs to route it, because the destination IP address is a remote server and not the firewall's IP address. And finally, the final point I want to make is, obviously, if the rule matches, but the action is to drop, the firewall inspection engine will drop the packet and not forward the packet to the networking layer. Let me repeat that. If the action is to drop the packet is not forward up the OSI layer, but instead, the inspection engine will drop the packet. I hope this helps clarify this firewall matching process. And so before ending the session, let's take a few moments to review the topics discussed in this module. First, we talked about Check Point being a software company. We make software that can run on many different kinds of operating systems, and also on open platforms. Open platforms are various supported third-party hardware. And then we talked about the Check Point Firewall Code, which is called the inspection engine. And the inspection engine gets installed deep into the kernel, and it shims itself in between layer 2 and layer 3. And next we discussed that the firewall is basically a router that's running the firewall software, and that nothing gets routed unless it's specifically allowed by the firewall's rule base. And finally, we talked about the first generation of firewall, which is packet filtering firewall, and how packet filtering firewall needs to have two rules. One rule to allow outbound traffic and a second rule to allow inbound traffic. And we also discussed that packet filtering firewall only checks the packet's layer 3 and layer 4 header information, and then it compares it and matches it to a rule in a rule base. And we also mentioned that all traffic is dropped unless it's specifically allowed by the firewall's rule base.
I hope you found this video informative. I hope to see you in the next video. Until then, shalom and bye for now.
Checkpoint. We secure the future.